Okay, okay, so let's start this session. Today we have Pietro BONFA, who will give a lecture about quantum espresso on high-performance computing and GPU systems, parallelization and hybrid architectures. So as usual, keep your questions at the end of the talk. When Pietro finishes speaking, I think we will have room for one or two questions on voice, so you can raise a hand and I will let you speak. And also you can write on Slack as usual, and we will report your questions from the streaming. So I think we can start. Please, Pietro.
Thank you, Ivan. Thanks for this opportunity. I'm very happy to be here and spend this couple of hours, slightly more, telling you something about how quantum espresso has been developed over the years in order to efficiently exploit and run on HPC and hybrid systems. So the topic that I will cover today is certainly quite different from the one that you saw in the previous lectures. And I believe that most of you may be not so familiar with the HPC system or hybrid system. So I try to make a very short introduction to how you do and you execute programs in these environments. And I try to keep the technical details to the strict minimum, but I believe that understanding a little bit how quantum espresso is really exploiting multiple cores, multiple nodes or accelerators allows you to predict the time that your simulation will take, and more importantly, probably, if you are exploiting your resources correctly. And well, first of all, let me start with kind of a joke, or let's say a game, because basically why you should bother. I was studying a few days ago. I had an idea. I was performing a simulation. I tried with a simple toy model, and I did what you probably did in the last days. So I configured quantum espresso. I needed PW. I did it on my laptop, and without caring much about how quantum espresso was compiled and executed, well, it took me this time to run my simple example. And then in preparing these lectures, I created an optimized version of quantum espresso. I was using the optimal parameters. Now I'm being a little bit arrogant if I say that after these lectures, I will cover all the details. So this is probably not the case, but at least I hope that with the tricks and the details that I will share with you today, you will be able to improve the time to solution. And this is what I got on my laptop. Now you may say, well, why should I bother? I mean, why should I spend these 4 hours this morning to gain, well, just let's say a minute or so? And I agree with you. There are probably better ways to spend the time if this was the case. But as it usually happens, or at least when I'm lucky, sometimes it happens to me, you find an interesting result, and you want to find out if you can apply this to more interesting material, say some cutting edges, long with magnetic system with long magnetic orders, or a structure with a large supercell which has distortions. So it could be many things, and in general, you end up with your laptop not being powerful enough to run your simulation. So you end up on a HPC system, on a HPC node. And so I did the same. So basically, I got my Quantum Espresso very simply by doing /configure and make PW. And on this system, with this PW compiled like this, well, it took this amount of time. And if instead you optimize this compilation, and optimize the way Quantum can exploit both many core systems. Here there are 48 cores and accelerators. This is the amount that you can gain. And so I think it's pretty substantial, especially if the deadline is approaching. Now, let me finish quickly this game and go to the real topic of this lecture. The point is that Quantum Espresso has been developed over the years to really exploit at best both HPC system and hybrid system. And just to give you another suggestion, so another idea, for example, just going out of science, this I'm quoting here, an IT website, very well known, and in their work, they are using Quantum Espresso to benchmark various CPUs, meaning that the Quantum Espresso is really able to exploit efficiently at best the CPU, and you can use it to benchmark the CPU. So this is basically my task for today, how to run efficiently on this system, and showing you what are the parameters and what are the configuration options that you should be careful. But before doing so, I want to explain why and how these options impact the performances. And to do so, I need to introduce very briefly a few concepts, really a few concepts about parallel programming. Then I will move to how these concepts are implemented in Quantum Espresso. And in the last part of this talk, I will describe accelerated system. Now, accelerated systems, the way you run Quantum Espresso on accelerated system is quite different from the way you use it on a standard or conventional HPC system. So I will focus the attention on this particular issue in a separate section of the presentation. But of course, in general, you will need to optimize the execution both on the accelerator and on the CPU. So this is something that we will cover in the final part of the of this presentation, and probably also in the hands-on. Okay, so first step. Now let me start with a disclaimer here. I will not introduce a general description of parallel computing. I will only introduce the concepts that are useful to understand how Quantum Espresso exploits multiple workers. In our case, we will be starting with multiple cores, but I will focus on the way Quantum Espresso is really implementing parallel options, parallel computing techniques, and not provide you a general overview. The parallel programs can be written in very different ways, and I will therefore only describe this concept in light of the way they have been introduced in Quantum Espresso. So, well, first is a very general statement, which is Amdahl's law, which is quite bad news for us. And let me go through this quickly, but because it's a very simple concept, but it's useful to well, actually, to start with some bad news, think of a task that takes the time t to run. Okay, and let me give you an example, because I will use this example later on when we will be dealing with something more difficult. Our task could be, for example, adding numbers in a file. Very simple task. So I have my file with a number of a list of numbers, and so this is my file, and the task I want to do is sum all these numbers. And there are two things that I have to do. First, read the file. Next, do the sum. If I have a single worker, say a single core, this task may take the time t. Now, I want to do it faster. How can I improve the performance? Well, there is a portion of this task that can take advantage of multiple workers. But there is also a portion that doesn't really take advantage of for having multiple cores in our case. Because when you read a file in a simplified, but not too much, not too much, in a simplified picture, but close to reality, when you read a file, having more cores is not really an advantage. You just have to wait for the hard drive to access the data and provide them and put them in the memory. So that portion doesn't really benefit for having multiple workers. While instead, if you need to sum these numbers, well, you can easily think of an algorithm that splits this list, for example, in two, if you have two workers, and assigns the first set of data to the first worker, the second set to the second worker, and hopefully in this way, this portion of our original task will take half the time. So it will become S time faster. S is the speed up of the portion of our original task that can be can benefit from parallel execution, right? Now let's go back and think how our original task will take if we use two workers instead of one. Well, that is very simple. There will be a portion of our task, that cannot take advantage of having multiple workers, and another portion, the original time was t, so p times t, that will be s time faster, so the time will be divided by, s. So in our previous example, will be just divided by 2. And of course, this is an ideal situation where you can make this portion of task arbitrarily faster. So it can become, the more workers you add linearly, it becomes faster. Clearly, this is an approximation. If you have like 6 numbers and 7 workers, well, the last one will do nothing. There is nothing. Or even if you have 6, basically, they don't have nothing to sum, actually. But let's stay with this approximation for the time being. Now, this is quite a concern for us, because this means that the speed up of your original task, the time it took when you had 1 worker and the time it takes when you put more workers at play, is basically will be basically defined by the portion of time that you cannot accelerate. And well, this doesn't seem a problem at the beginning, but think of a very so you have your program and you've been very good. You have changed it in a way that for the 95% of the time, it can exploit multiple workers in an ideal way. Like you have 4 workers, the portion that can be parallelized is 1/3 of the original time. Well, even if you do so, the maximum speed up, so the time it will take with respect to the speed up is this one. So the new time, the time it will take once you have accelerated it, will make the parallel portion working ideally well. Well, the maximum speed that we will obtain is 20 So you are really, of course, just paying the price of having 5% of your program not being working in parallel. And okay, this is a very bad news because, well, it tells us that we will have to be extremely good and work out parallel algorithms that work extremely well for basically all the tasks in our program. And moreover, well, we have been discussing the case where the parallel tasks can benefit from multiple workers of any number, but in general, this will not be the real situation. And some tasks will start to become, will start to enter the portion that cannot be further accelerated once you put more workers at play. So this is the situation we are dealing with. And therefore, our task now is to organize basically all the work that Quantum Espresso has to perform in algorithms that can be executed by workers in parallel. Now, how is Quantum Espresso doing this? Quantum Espresso uses mainly uses the message passing approach. Now, let me spend a couple of words about this. What is message passing? You probably have seen this command before, MPI run. MPI run, in the example that I'm showing here, starts a program 3 times. So I could have here, instead of PW, I could put whatever other program I want. I could put, for example, host name, okay? What would happen if I run this command? It would print host name, the host name of the machine I'm working on, 3 times, nothing really. But instead, what happens when you start Quantum PW? Well, of course, starting the application is not the only thing that message passing provides to the application. It does 2 other things. It gives a label to my executables, and therefore these programs will have a label that they know, and gives the possibility of sending messages. That is in our that basically is all it does, because all our application or our PW processes, that's how they are called, will be independent from each other. So they will be separated by what I'm showing here as a wall. They will not know about the other instances that are running unless they send messages. Messages can be, well, they are just sending data. They could be whatever you want. Like, for example, you can imagine that the yellow here, Mr. Yellow PW, yellow one, is reading the input and sending it to the other PW instances. But you could also have Mr. Yellow here sending data to Mr. Green, okay? And of course, the larger is the message, the more time it will take to be delivered. It's very easy to guess. And well, of course, if you think about what I was saying before, you need algorithms that can can exploit very well multiple workers in parallel. I think in these days you have experienced working in parallel, in separated environments. You have a job to do. You do a Zoom meeting, for example. You spend time doing many Zoom meetings, but the work doesn't get done. So clearly, communicating is a way to organize jobs and works, but doesn't get the job done. It's additional time that generally is useful to organize work, but can delay the execution of the real job that you have to do. And well, as I said, there are a number of messages. You could also have, you have also the option to synchronize your executions that otherwise go freely. Each one will proceed in time freely until they find some point where we want to synchronize. And the last concept, which is not useful for us, but I have to mention it because it appears in the output of Quantum Espresso, so you know what it means. You also have the possibility to create groups. Now, groups is nothing really useful from our point of view. You have labels. You have labels already, so you could just say that my group is 0 and 1, and that would be enough. But in order to simplify the organization, in general, you create groups that can exchange messages, and this is just a way to easily identify the workers that are assigned to a given task. Now, of course, workers need resources to run. And this is how it goes. Basically, in a multi-core system, you assign your process to a core. And this is actually done by MPI run. If there are enough cores, you shouldn't be too worried, at least for the time being, which core is selected and how it is assigned to PW. But all your instances or your processes will also allocate some memory. And now the point that I want to make here is that it's not that they have a real piece of hardware they have been assigned to. They will ask for memory spaces, but these memory spaces are assigned to a given process and cannot be seen by the others, okay? So if you want, for example, if Mr. Yellow here wants to know something that Mr. Green has, well, it has to send a message and ask for it. And the message, the data will be moved from the memory through this message to the second, to Mr. Yellow here, that will store it in his own portion of memory that he has previously allocated. Okay, and now the question probably. So the first time I saw this, I thought, but this is absurd. This makes no sense. Why should I think of these objects as separate entities that should exchange messages? Well, I have a system which is made of many cores and all of them are attached to the memory. So why should I create these very funny separated processes that can only talk with messages? And well, that's of course the case when you are dealing with a single node, but in general, you are running Quantum Espresso on many nodes. And in this way, the only thing that you have to guarantee is that your workers can communicate. So the only thing that you have to guarantee is that there is a channel allowing communication between the multiple nodes where your MPI processes are placed. And basically, this is the reason why Quantum Espresso has been originally developed using message passing. In this way, you can place your processes anywhere on a large HPC system, and the only thing that you are to provide is a communication channel. And clearly, you gain if the communication channel is fast. So in general, having all the processing on a single node allows for fast communications because, well, you just have to move the data from one portion of memory to another portion of memory. While instead, in this case, you probably would have a network device doing the communication. But no matter what, you have whatever channel of communication you have, you can run on multiple processes separated on different nodes in your system. And this is how Quantum Espresso has been structure from working in parallel on a series of tasks. Now, let me move to a little bit more advanced topic. And of course, you still may think that this makes no sense. and you want really to exploit the fact that you have many cores on a single node. And for this reason, also a different approach has been implemented. And this is the approach called OpenMP. And this is a totally different idea. In this case, you start, for example, I'm starting one process, the PW application here. And it will do some work. For example, here it will run alone and allocate some memory. Let me draw it here. And then it will eventually arrive to the point where it has some work to do, and it decides to exploit multiple workers. So the number that you specify with this command, oh, this should be not capital E, that's PowerPoint messing up. Well, the number that you specify here is the number of workers that you want to be created when you want to work in parallel on a given task. So you will have 3, these are called threads working in parallel on a given task. And the real difference here is that the memory allocated previously can now be accessed from all our 3 workers, no messages to be shared, and clearly this makes sense, but of course you are limited by the fact that all your workers or your core needs to be able to access the memory, the same memory. And this is not true when you have cores spread on different computers, on different nodes. And well, the only additional point that I want to make clear is that, of course, even if you start with a single process, so even if at the beginning you need only a single core to do the work, when the parallel region where the job needs to be, when you need to get the job done and you create these 3 workers, each of them must have some resources to run, so a CPU core to run. And if you don't do so, so if you just provide a single CPU, well, this will be competing for resources on the single CPU that they have been assigned to, and this will make the job even slower because they will working partially, all of 3 of them on the same CPU, but also spend time deciding which one has to do the job. So never forget to assign the required amount of compute power when you also enable OpenMP. And this seems rather trivial, but generally a mistake that I've seen, because what you will be doing in the hands-on in the next 2 hours is running with both MPI and OpenMP. And therefore, you need to grant enough resources for both the OpenMP threads that may be created during the execution of each MPI process for all the MPI process. So if you go back and watch the slide you had before, now you need 3 cores for each process and a total of 9 cores in the example that I'm showing here. This is a bit complicated, probably, but I hope that I made myself clear on the important point that I just said. Now, let me go back and simplify the picture, because as I told you, Quantum Espresso has been really organized, thinking of messages going around. So for the time being, let me focus only on a number of PW, and I will mainly talk about PW in the next slide. So let's focus on this program that does solves the Kohn-Sham problem and gives you the ground state electron density and energy, total energy. So let's think of this situation here. We have a number of PW executors that can send messages around to organize the job and share, and possibly share also data. Not really share, send data. So the question now is, we want to get the job done. Like, remember the example that we was quoting before, the sum of a list of numbers. What did we do? The thing that we did actually was to identify a way to split our initial set of data and give it to a number of workers that had to do the job all together in parallel. And that's indeed what we want to do now. We want to focus on, let's start focusing on the data rather than on the task, and think how we can give some data to our workers in order to get the job done. What is the job this time? The job is, well, solving the Kohn-Sham equation, but eventually what we want to do, and I stole this slide from Paolo, which provided the great introduction to what I want to say today. Hopefully it will be a little bit more technical than what he said, but I hope I'll make examples easy enough for you to understand. So I was saying, what I want really to compute is this, okay? So this is the, well, the density. You have seen the details of how to make it symmetric, but let me just say that this is the density, and this is the whole amount of information that I want to compute over the time and eventually to obtain. And this will give me also the total energy. And so let's think of this in a different way, in a different, with the idea of making this data, splitting this data and giving it to multiple workers that can work on this at the same time. So let's look how this, how you build this. You build this by considering a number of K points in the first Brillouin zone. Actually, if you have symmetry, you consider the irreducible Brillouin zone, so a portion of it, and you will have to solve the Kohn-Sham problem for a number of K points. And of course, you will also need to solve it for a number of bands. So in the case of the density, you need the valence states, but in general, you will have a number of bands that you will considering. And finally, what you need is, as it's evident here, the wave function. And the wave function itself is defined as an expansion of plane waves. So here you have a lot of data that you are storing somewhere to define the wave function. Okay, so these three sums that appear here basically identify the whole amount of data that sooner or later you have to deal with when you want to compute the density. So let's visualize this and think of how we can give these data and split this data to have multiple workers dealing with the Kohn-Sham problem at the same time. Now, the first thing you may, the first idea that may came to your mind is that, well, you've seen Bloch's theorem, you know that you can solve the Kohn-Sham Hamiltonian in our case, in the case of plane waves and periodic boundary condition, at different K points independently. So you think, well, I have a smart idea. I will cut this whole set of information. Oops. Let's use a different color like this. I will cut this set of information along these lines and have my, well, let's say, 4 workers, or well, it's 3 here, work on different k points at the same time. They will solve the Kohn-Sham equations at different k points at the same time. And this makes sense. And indeed, we will come back on this, but think about it twice. You are going to a supercomputer, so a system that has a large compute power. You are probably dealing with a material which has many electrons or a large number of atoms. And so it's probably, it has a large unit cell. So this means that the reciprocal space is instead quite small. And the larger the real space is, the smaller the reciprocal space becomes. So the number of k points that you will be dealing with becomes smaller and smaller. And therefore, the workers, some workers, will eventually have nothing to do. Like you will eventually come with only using the gamma point. So there is no work to distribute at all. So, okay, let's forget about this idea for the time being and look at another direction. There is another direction that is probably interesting, the number of Kohn-Sham states. And well, again, let me put this simple. I will come back probably on this at the end or during the hands-on, but let's make it simple. The number of Kohn-Sham states is of the order of, on a system that you may run on a single node, is of the order of, well, 100 or something of that order of magnitude. And the number of cores that you have on a single node today is of the same order of magnitude. So don't really want to waste time. You can immediately see here that the real tall dimension is this one, is the number of coefficients, the expansion in plane waves that you have for your wave function. And that's indeed what guarantees that you have enough data for each of your worker to do some portion of the job. And that's indeed what QuantumEspresso is doing by default. And this is great because how it goes is more or less like this. You have your 4 workers, in this case, working on the first K point. Let me write here K1. And they will work together on the first K point, and they will have a fraction of the wave function. And once they are done with this, they will done with this K point. So they have all the bands or the Kohn-Sham state. They will move to the second K point, let me call it K2. And again, they will all work together, having a fraction of the wave function. And so first worker will have this fraction here, second worker will have this fraction here, but they will be working together and eventually synchronize and move to the next K point. And so on. Now, this, as I said, is what QuantumEspresso is doing by default and works pretty well because that's the total dimension of this total amount of information that we want to collect. But there is a problem with this, and this leads to quite a lot of communication. You see that QuantumEspresso is built using message passing. So a lot of messages are spread and are sent with this approach. I will come back on this later, and I will try to explain why this is the case. But for the time being, let me just tell you that this works great, but we have a problem with the number of messages that is growing fast. So let's go back to our original idea. Our original idea was to split the number of K points. And so how will this go? Well, we will have like 4 Ks, like I'm showing here, K3 and K4. And we will have our 4 workers dealing with entire wave functions and working at the same time on the problem, on the connection problem, at different k points. And so all my 4 workers will have at the same time all the wave function, and will be working at the same time on the connection problem at these 4 k points. Now, for a reason that, again, I will say in a second, this reduces the communication. But there are 2 problems with this. One is immediately clear. You have now the 4 workers working at the same time on the 4 k points, and each of them will need to allocate the entire wave function. What we said before is that our 4 workers all of them were acting on the first k points, and they all had fraction of the wave function. So the whole amount of memory that was allocated in this first case was this fraction plus this fraction plus this fraction. So 4 fractions making an entire wave function. In this case, you have an entire wave function for the worker that is working on k.1, and an entire wave function on the worker that is working on k.2, and so on. So clearly, there is much more memory being used in this case. And this can be a problem. Generally, you have enough memory to exploit this, but you may also run out of memory and being unable to load all these wave functions at the same time. And this is something that we will investigate further during the hands-on. But there is one additional problem here. So think of the case where you have, I don't know, like the total number of k points being 6, and you have your usual 4 workers, right? So the first worker will have, how do you do in this scheme that I'm showing here? Well, it's simple. You assign 2 k points to the first worker, 2 k points to the second worker, 1 k point to the third, and 1 to the fourth. And then when they're done, you will have the entire knowledge. Of course, they will have computed all the states, all the bands, so you will have the entire knowledge you were seeking before. But the problem here is that these 2 guys here will take care of 1 k point, and these 2 guys as well. But then these 2, when they are done with the first k point, have nothing to do, while these 2 still have to do an additional k point. So we'll have half of your processes being idle, while the other one are still working on the conditional equation on a given k point. So this is something that goes under the name of load unbalance. Oops, no, sorry. Load unbalance is not good, it's bad. And you should be careful about this because leaving some processes idle clearly doesn't get the job done. So what you end up doing, and what you will be doing in your exercises, is, well, just trying to find the best compromise. So working with both options and getting the job done by solving the Kohn-Sham problems on multiple k points in parallel, but also splitting the wave function among multiple workers. And you will have to find the compromise that reduces both communication, memory usage, and load unbalance. And this is in general far from trivial, and there are some strategies to tackle this problem, and you can easily find actually a good starting point, but finding the best, really the best time to solution, that in general is not so trivial. Now, give me a second. Okay. So, okay, now I want to attempt something difficult, and that is explain or try to explain the problem with communication. Now, this is a little bit, quite an advanced topic. So if I fail to let you understand this point, to make you understand this point, just keep in mind that with the parallelism on K point, you reduce the communication, and otherwise, if you don't use it, there are quite a lot of messages going around. But let me try to explain why this happens. Again, I'm stealing a slide from Professor Giannozzi's lecture on day 2, and I hope he doesn't mind, but this way you can also go back and revisit my starting point. My starting point is the dual space technique that you have been introduced quite a few days ago. So the idea that you can compute this application of the Hamiltonian on the wave function by working in the space that is but the best space for all the operations. So the reciprocal space for the kinetic part, and for example, the real space for the local part of the Kohn-Sham potentials. And you have also seen how to do this quickly with the FFTs on discrete grids. Now let me quickly estimate how many times you are doing this. Basically, how many times you are, how many FFTs you are doing. Let's say you start from reciprocal space and you want to compute this term here, that really is one of the most time consuming part on this task that I'm showing here. So how many FFTs you will be doing? Well, you will have to do it for a number of Kohn-Sham states times a number of K points. And you will be doing it for time for many iterations. So I can add here a number of iterations. So if you do this product, this is of the order of, let's say, 100, this is of the order of 10. And if you're lucky, this is also of the order of 10. And this is already 10 to the power of 4. Now, to be honest, and there is also factor 2 because you are going from G space, from G space to real space and back to G space when you want to add all these terms. And to be honest, here also there are other factors. So, but even if you forget about this, still we are doing really a lot of FFTs. And let's think how these FFTs can be done if we have the wave function separated and in the memory of different workers, different processes, MPI processes. Now, to simplify this picture, you've seen again on day 2 how you can write the density as a function of plane waves. And let me talk about density. The concept is exactly the same if I talk about the plane wave expansion, but of a block state. But let me talk about this because it's easier to visualize. Certainly easy to visualize. It's a real quantity you have, and you can clearly imagine it to be in real space. What I'm showing here is real space, okay, and discretized on a grid. Okay, this is something you heard probably on the second day. And so you have your density in real space. And how, so this is your data now. This picture here has nothing to do with the matrix that I was showing before. This is now, let me say, for example, the density, but could also be the plane wave expansion of the wave function. But I think it's easier to visualize it with thinking of a density. It's a real quantity on a grid, something that you can really see. And how do you distribute this data among many workers? Well, you certainly have a smart idea. You have a set of points, a grid, and suppose you have many points in these planes, but 4 planes, and you also have 4 workers. So the idea is that again, the worker, the MPI process that now I call Mr. Green will have the first plane on our grid of 4 planes. Mr. Blue will have the second plane. Mr. Red will have the third plane, and Mr. Yellow here will have the 4th plane. So you're done. You've been distributing this real space data among many processes, among your workers. And now you ask them to do the FFT, and they send a message and they share the fact that it's time to do the FFT. This is a very small message. Right? Just do the FFT, guys. So they will start, and they all start with the X direction. So they will all compute together the X direction. And then they will move to the second direction here. And this is something they can do on their own. They don't have to share messages. They do the FFT. I hope you know that if you want to do the FFT in 3 dimensions, you can do it with 3 1D FFTs along the various directions. And so they've done all of them independently did the FFT along X and Y, but now it's time to do the FFT along Z. And here comes the problem, because none of them has the data on Z. They only have a fraction of the data. So they cannot do the FFT, the sum of the FFT that you have been introducing the second day. So how can they do that? Well, here comes the smart trick. It works like this. So Mr. Green here tells all the other, okay, guys, send me the column that I'm drawing here. Send me this first column, and I will take care of doing the FFT on this first column along the Z direction of the data. And Mr. Blue does the same, and it tells to everybody, well, send me the second column here. Okay, and I will take care of doing that. And it goes on like this. Now, probably this drawing is not very accurate, it's too small, but what happens is that we'll all ask for data and compute portions along the Z direction. So they will eventually have columns in reciprocal space. And these columns, as you have seen, well, they are really in, of course, again, on a cube system, but the relevant data are not on a cube. They are selected. The relevant G vectors are selected by the cutoff. We have 4 times the cutoff energy, the cutoff energy if you're dealing with a density. Let me forget about ultra soft pseudo potential for the time being. You have 4 times the cutoff if you're dealing with a density, the energy cutoff. Instead, we have a radius which is half the second radius if we are dealing with a wave function. But that's the point. You will have columns, and these columns are called sticks in the quantum espresso output. And that's where they come from. But the point I wanted to make is that, as you have seen, when you want to compute an FFT at a point, all your workers will have to ask to all the other workers to send some data. And this is not a message like, let's do the FFT. This is a message where you send the data, your wave function or your density to the other workers. And this is one of the most time-consuming operations that you can do. This is called an all-to-all operation. So all processes are sending messages to all the others to get the job done. So they are spending quite a lot of time communicating. And the more communication you have to do, the longer they will take. The message will probably be short, smaller, but you still have a lot of communication with a lot of people to send or receive data from. And just to tell you where this appears in the output, it's in the top, and I hope that you now understand what this stick is. And just to give you some order of magnitude, this is an example I was working on a few days ago. This is BCC Iron. I was working with that running with 16 processors. So this is the number of sticks, total number of sticks that I had. And this is how they are distributed among my 16 workers. Some of them have 13 sticks, some of them have 14 sticks. And when they're doing the Z direction, they are really like performing a few, this is the number of FFTs that they were performing along the Z direction with a size that is really tens of elements. So this is really something small for your system, and you will be, if you add too many workers, you will be doing a few small FFTs and then sending messages around quite a lot. So a number to keep to check when you're running simulation is certainly the number of sticks that each of your workers is dealing with. If this becomes too small, they will be doing very small FFTs and communicating a lot of data quite often. Okay, so I don't know if this is clear enough, but I will not go into any further details right now. And let me instead summarize what we've been talking about till now. We've been talking about the possibility of solving the connection problems in parallel of multiple K points. And we've been talking about the possibility of splitting the data, the wave function on multiple workers and work with fraction, with our worker working with fraction of the wave functions at the same time on the same K point. Now, this, and I told you that you in general have to use both these options at the same time. But really what you do is selecting this option here. And QuantumEspresso has a hierarchical set of parallel levels that are used to organize the work. So you start with all your MPI processes, all your PW executables running, and you decide how many groups of workers you want to have working on K points. So let's make this simple. Let's think we have 6 K points, and you have and you decide to have 3 workers working on each K point. This first group will work on K point 1 and 2. This second group will work on K points 3 and 4, and this one on 5 and 6. But you may have more processes. So inside each group, the workers will split the wave function on G vectors. And this is what is called in the QuantumEspresso output the band group. Now, group refers to the thing I was saying at the beginning of the lecture, how you organize your MPI processes, which are your workers. And band refers to the fact that you are splitting the wave function on G vectors. Well, now it's really late, so I have a couple of additional information that I want to tell you about conventional HPC systems, and this regards additional level of fine-grained parallelization that we can tune, and this is the topic that we'll cover next. Let me just add one more point and be general enough for my presentation to reflect what actually is the distribution of MPI processes. So what I've told you is what happens for pw.x. So plain wave code, but this is not the only code that you have in QuantumEspresso suite, and there are codes that can exploit other level of parallelism, which is specific to their task. And you will also find this image group that can be used to split all the workers on different tasks. And I will go back to this later, but now let me move to this last part here in PowerPoint. And I have to talk a little bit about how you actually compute the eigenpairs of your Kohn-Sham Hamiltonian. Now, I think you heard or you know that when we're working in plane waves, yes, we do have a basis set, plane waves, and we could in principle just solve the circular equation and find the eigenvectors and the eigenstates and the eigenvalues. So why don't we do that? Well, we don't do that because we have a huge number of bases. We have a huge number of plane waves, and doing so would be, well, maybe not even possible, but in any case, very slow. So what you actually do in plane wave codes is iterative diagonalization. Now, I certainly don't have the time to enter into the details now because it's almost an hour that I've been talking. But I want to mention that you have many options to do this iterative diagonalization, and and I will tell something about very briefly about this approach, the Davidson approach. But this is a field where active developments are really going on these days in Quantum Espresso. So keep an eye on this, because these different options for the iterative diagonalization grants different speed or memory consumption, and also scale different when you work on multiple, with a growing number of workers. So Davidson is what is selected by default, and that's the reason why I will spend some time, well, one slide on it. But if you need to save memory, you may opt for the conjugate gradient approach, which is much slower, but allows you to save some memory. But the really new options are coming that can optimize both memory allocation and speed. So you can certainly initially go with Davidson, but if you find yourself in need of saving some gigabytes of memory, you may consider also other options. Now, I want to tell you very briefly something about the iterative diagonalization done with Davidson, because that brings me to an important option that you have to tune when you run on large systems, on HPC systems, with large input files, let's say, on HPC systems. So how do you solve the Kohn-Sham problem? How do you find the eigenpairs of the Kohn-Sham problem when you are working with a plane wave-based code? Well, what you actually do is that you start with a guess of your eigenpairs. And if you are super lucky, but that basically never happens, these are already your eigenstate. Well, instead, Ernest Davidson came out with an idea for extending the space where you look for the solution of your Kohn-Sham Hamiltonian, and therefore what you actually end up doing is computing the so applying, as was said on second by Professor Giannozzi, computing the Kohn-Sham Hamiltonian on a set of states which is of the order of the number of Kohn-Sham states. Well, actually a bit more than that. This is your initial guess. Then you can expand it with additional vectors and consider this reduced space where you look for the eigenstates with the lowest energy. And therefore, what you end up computing in the Davidson method is a generalized eigenvalue problem. And I don't want to enter here too much on the details. What I really want to focus the attention on is the fact that you're dealing with a set of states, and therefore an eigenvalue problem which has the dimension of a few times the number of Kohn-Sham states that you have in your system. And you may say, well, that's fantastic. We started from a huge number of plane waves. Now we're dealing with things that are of the order of matrix sizes that are of the order of hundreds of elements in somehow small inputs. and this is true, but when you start, so basically, this is to say that you shouldn't be worried about this problem, this generalized eigenvalue problem that you have to solve. This hundreds of elements will take milliseconds, fractions of the seconds to compute, really small fraction of the seconds to compute on every single core machine that you may have. But when you have larger inputs, this eigenvalue problem can become larger. And yeah, I've been trying this a few days ago. I took well, this is something that I already knew, but I prepared this result a few days ago, considering the best library that I had on this system is an Intel-based system. And it doesn't matter the details now, but I used the best library that I had to solve this generalized eigenvalue problem with one core, and the best library that I have to solve the same problem, but with many cores at the same time. And well, you immediately see that, well, this is a problem that scales like the cube of the matrix size. And if you use a single core to solve the generalized eigenvalue problem, or use multiple cores, as the matrix becomes larger and larger, the difference becomes substantial. This is not even here, it's going up somewhere. So if you forget about this on a system which are large enough, and now you should look at this number and check that I'm having here matrices of the order of 1,000 elements. So we're talking about, we are talking about a system that has hundreds of Kohn-Sham states. Well, if you forget about diagonalizing the dense eigenvalue problem in, so the eigenvalue problem on the subspace in parallel, you are really losing quite a lot of performance. But at the same time, most of your simulations, if you're dealing with small input sizes, are on this side of this graph. So on this side, you really lose quite a lot of time if you use a parallel eigenvalue solver. It's much more efficient to use a single core. So the final message here is that you should really and certainly use parallel eigensolver if you're dealing with large inputs, meaning hundreds of Kohn-Sham states, while you should definitely avoid it if you're dealing with small system, tens of Kohn-Sham states. Okay, so I think that I'm really late, so I will not tell you much about OpenMP because I think that Ivan will cover this during the hands-on. So maybe it's better if I just let him describe how OpenMP can be used to further improve the performance of the code. And so let me skip this and mention instead the image option that I discussed before. So for example, the image option in this hierarchical organization of work that I was discussing is the first one. So the first level of splitting of the job to be done. What you have, for example, in NEB or on the phonon cone is that images correspond to tasks that require very little communication, like, for example, the computation of the forces in the images of NEB simulation or the reducible mode in phonon simulation. So this image parallelism is really a sort of abstract layer for tasks that do not really require much communication and can be used at the topmost level to start splitting the work to be done among the many workers. And below that stage, if you're dealing with a problem that involves the computation of Kohn-Sham equation, you still have all the additional layers that I was showing before. So the subdivision of the work on k points and the subdivision of the wave function on the band group, in the band groups. And okay, so in the very last part of this discussion on systems, with an HPC system, conventional type, let's say, not accelerated ones, I very briefly mentioned how you can really exploit all these options that I've been discussing. So the image parallelism is activated with this option here, and here I give you the example for NEB. And well, what you should put here in the I, well, clearly this is a parallelization strategy that requires very little communication, so it's very good, but in general leads to more memory allocation. So you should use the largest possible value, but that is not always possible, and you should experiment really, and check if you have enough memory to use what I suggest as the best option. Then pool parallelism. Now, pool is probably some of you a bit misleading, but this is just how many workers will be, how many groups of workers will be created working on multiple k points at a time. So basically, this will create X groups of workers that will compute each of them a different, the Kohn-Sham Hamiltonian at a different k points at the same time. And as I told you, this reduces communication, and therefore you should exploit it as much as possible. But this is again not always possible. Clearly, you need to provide at least 1 point per pool, otherwise your pool of processor will have nothing to do. But also, as I told you, this leads to memory duplication, not duplication, to larger memory allocations. Therefore, you are sometimes limited by the amount of RAM available on your system. And this is the last thing I mentioned earlier. So the diagonalization, when, for example, in iterative diagonalization, in Davison iterative diagonalization, but that's not the only case. But in Davison, the most common, you have to do it in parallel where we are dealing with large systems. And I would say, let's say more than 100 Kohn-Sham states, order of magnitude. That really depends on the hardware. So it's not so easy to give an advice on this. Now, clearly, this number must be smaller than the band group size, meaning that if you have a number of pools working on the Kohn-Sham equation at different k points, each pool will have the so-called band group, if you've seen it before. So workers working, all of them working at the same time on the same k point, and they will have to diagonalize so to perform the iterative diagonalization, so to perform this eigenvalue problem. And so this number must be smaller than the group size, band group size. But this is something that the code takes, so you can put a large number here, and the code will find the best, no, not the best, the largest possible set of processor or processes, MPI processes working in parallel on the eigenvalue problem. This is not necessarily the best value that you can choose, but at least guarantees that you're not solving this in serial, so with a single core when you have large problems, but instead remember to use a single core where you have small problems. And well, that is basically, that is it for the parallelization of quantum espresso on standard or conventional HPC systems is it's certainly far from trivial, and I hope that now the options that you have make a little bit more sense, at least these two, and finding the optimal solution is really a matter of balancing between the memory usage and the amount of communication that is required between your MPI processes. And probably this will become a little bit more clear during the hands-on. Now, before it's too late, let me mention one important thing. And as I said at the beginning, if you just do /configure, you may be lucky, but you may even not be lucky. What Quantum Espresso does is trying to find the set of libraries to perform the operations that the algorithms requires. So basically linear algebra and FFTs, but it may well be that it doesn't find anything and uses the versions that it has embedded in the package. Now these are very bad, definitely not optimized for the systems that you may have. They're just meant to have something is running no matter what, but you should really look for libraries that can perform effectively on the system where you are trying to build Quantum Espresso to do your simulations. And I'm showing here a number of open source options that can be used to do linear algebra, FFTs, and parallel eigensolvers basically on many clusters. This is the minimum that, at least this is the minimum that you should be looking for. And if you plan to deal with large inputs, parallel eigensolver like Spark is certainly required. If you are dealing with an Intel-based system, you have the MKL library, and this provides you with all you need for effectively running, compiling Quantum Espresso with the best, something close to the best possible performance. It provides you with linear algebra, FFTs, and parallel eigensolver. And you may also exploit this library on AMD system with some tricks. And there is also these options with the AMD libraries, which is still, not much explored. But if you are on an Intel-based system, definitely MKL is the way to go. Or if you want open source option, that's this. This is the set that you may check. Okay, last word of advice. Also, when you write to disk, Quantum Espresso write quite a lot of data to disk, and you have the option out there in your input. Well, you know that HPC system, in a HPC system, you need to access all the files from all the nodes, and this parallel file system is nothing but a parallel application, and it has been optimized different purposes. So always remember to use the scratch space when you are storing a lot of, and in this case for Quantum Espresso, this is what is done. This is what is done during the simulation, and stored and saved in the folder indicated in out here. Okay, in the 15 minutes that I still have, I will finally discuss something about GPU acceleration and GPU acceleration in Quantum Espresso. Now, let me give you a very brief introduction to this and explain why we decided to add GPU acceleration to Quantum Espresso. Well, you can see that a number of systems in the top 10 HPC system in the world. This is a list taken from the top 500 website, and these are the 10 most powerful HPC systems in the world, and a number of them, I think there should be 6 out of 10. Let's see if I find all of them. Voila. They are adopting GPUs. And the reason why is that now, if you come back to this slide and compare the peak performance and the power that is required to achieve this peak performance, you will notice that if you use GPUs, you generally obtain a nice reduction in the energy that you need to run your system. Now, you don't pay the bills, but who pays the bills probably is interested in this. And therefore, many GPU systems are appearing on this top 500 list. And how can the GPU make this magic? How can it magically reduce the power that's required? Well, it does it, it's not magic, it does it by changing the structure of the architecture of the device. Basically, it is devoting many more transistors to the arithmetic and logic units, so the one that do the computation. And therefore, where is the other part of the CPU gone? So where is the pipeline? Where is the thing that controls the execution? Well, it's smaller, much smaller, and who is doing that work then? The developers are doing that works, and it takes quite more effort, more effort to develop codes for the GPU than the CPU. And you are lucky actually, because the developers of QuantumEspresso did it for you. And what you only have to care is a few details about CUDA programming, which is the language that has been used to accelerate QuantumEspresso to GPU. And let me skip this slide because it's not so important. And I will tell you instead that, well, a thing that you may need to know and remember is that when you create and compile QuantumEspresso to run on GPUs, you will make a very specific executable that can only run on a specific version of on a specific card, which has a specific architecture. And this is summarized in the so-called compute capabilities. And that's a number that you can check online, find online. And this is still a number that you will have to specify when building QuantumEspresso for GPUs. And we will go through this during the hands-on. Now, you are lucky because in order to build QuantumEspresso, you need the NVIDIA HPC SDK, and it embeds all the compilers and all the libraries that you need to efficiently build QuantumEspresso and exploit the GPU at best. And so during the hands-on, you will see really how this process is done, and is quite simple. But the message maybe here is that you really need to use this package. And for the time being, you cannot compile QuantumEspresso with other compilers or take advantage of accelerators different from NVIDIA ones. So the one that can be exploited with CUDA, actually. Now I think this will be, let's leave it for the, let's leave this for the hands-on. Probably Ivan will talk about this a little. And let's instead focus on what you can run on hybrid systems. Now, for the time being, all libraries of QuantumEspresso can take advantage of the presence of accelerators, and PWSCF, so the PW code, can be accelerated, is accelerated by GPUs. There is also an experimental port of NEB, but you should be careful. This is really a work in progress. So it's probably, if you wait a little bit more before trying NEB, but just so that you know that work is ongoing, and soon you will probably have additional programs ported to GPUs, because as you can see, these layers show you that the external packages depend on the internal ones, and therefore having accelerated PW will allow faster development for the other codes in these external rings. Now, another thing to keep in mind, and this is for a reason that I will discuss in a second, is that not all features of Quantum Espresso can take advantage of the accelerators. As you can see, the list is growing, and in version 6.6, quite a lot of features are accelerated and can run on GPUs, but some of them are still still running on the CPU, and some of them also, for example, the parallelization solver is not yet ported on the GPU. This may be a future, but really for GPUs, this is not a big deal, and we will see in a second why. But keep this in mind, and I will tell you in a second why this is important. Now let's, for example, look at a GPU card and discuss how Quantum Espresso is running when it is exploiting the power of a GPU. First of all, let's not focus on the computational power, but on memory. You see that, for example, on Marconi 100, you will have four, in a single node, you have 4 Tesla cards, and each of them has 16 gigabytes of memory. And if you, well, 16 times 4 is 64 gigabytes. And this is a much smaller number than the amount of memory that you have on a single node, which is probably 4 times larger. I don't remember exactly, but really much larger. And this tells you immediately that you will have to fight again harder to optimize the number of pools that you can fit on a single GPU card to optimize the parallel executions. Another aspect that I should mention is that the cores of your application are, the cores of your GPU are much slower than the cores of the CPU, but you have thousands of cores. So this clearly tells you that the amount of data, the amount of workers that you have, and therefore the amount of data that you have to provide, in general must be larger than the one that you are dealing with on the CPU. If you don't provide enough data, you will have workers being idle and running much slower than the worker on the CPU. So when you are trying to exploit a GPU, you will have to be, you will have to deal with inputs that are large enough, meaning that you are providing enough data for all your CUDA cores to work on. And this means that if you have small systems, you want to compute, for example, you want to do some high throughput computing with small input, the GPUs may not give you a real boost in performance. But now let's focus on how you run Quantum Espresso on hybrid systems, on accelerated systems. And I'm considering here the example of Marconi 100, but you do find similar architectures in many HPC systems, or probably also in in various workstations. So, but the example of Marconi 100 is a bit extreme, and also it's not unconventional, but certainly is useful to understand one problem here. So if you look at the entire CPU, you see that the power that it provides, the computational power, the number of floating point operation that does per second is 700 gigaflops. Well, that of the whole set of accelerators is 31.2. Now, look at this ratio. I mean, the whole set of cores in the CPU, you have 32 cores in this machine. So these 32 cores, oops, there's 32, no. The 32 cores in your node are just providing basically 1/10 of a single GPU, which is about 8 teraflops, you see. So a single GPU is 10 times faster, and the entire power, computational power, comes from the GPU. So this means that if we want to run if you want to run Quantum Espresso efficiently, well, we must really forget about GPUs and use the same machinery that we created for the CPUs now for the GPUs. And this means that our processes that we are running with MPI run and have been organized in such a way to split the job to be done and split the data and work on a given task together. Well, these MPI processes now will have to use the real source of compute power, which is the GPU. So this clearly tells you that you will want to associate each process with a single GPU. And therefore, in general, you will be running Quantum Espresso quite differently from what you would do on a standard HPC system, where you have, I don't know, tens of cores, like 24, 48. Now, instead, here in general, you have a few GPUs, so we run just with a few MPI processes, and these have already internally, the PW or executable, for example, internally already organizes the work and will allocate the tasks to the various GPUs where the computational power comes from. And this is nice, would be nice, but actually to run on a GPU, you also need a CPU. And there is also an additional point probably, and is the fact that not all tasks can benefit from the GPU, and not all tasks, I told you before, have been ported to the GPU. So when you're running with PW in this way, you will still have a few portions of your problem, a few tasks that are still running on the CPU. And they're running on the CPU quite badly, because the process will be assigned to a core, and this core will control the GPU, which is really doing the job here whenever we have an accelerated version of a given algorithm. But where we don't have a single core working to get the job done for each process. This is quite bad, but you can overcome this by exploiting OpenMP parallelism, and this way add multiple cores for each MPI process. But this is again something a bit more advanced that we will cover in the hands-on. The important message is that the machinery that we prepare with message passing and therefore each MPI process that organizes the work with this message passing architecture should be assigned to a single GPU. That is where the computational power comes from. And so this is basically, this is the message that I just discussed. Yes, also there is no parallel eigensolver right now, but this may change in the near future. But this in general, except for very large input, doesn't represent a problem. Now, it's getting quite late, so I had a few more slides to discuss. So maybe I can just fly and just this is just a few best practices, I would say. So these are the set of options that you have to keep in mind when building Quantum Espresso on HPC systems. So as you will see, it's better not forgetting about OpenMP, especially if you're dealing with hybrid architectures. And you enable CUDA with this set of options, and you should do it explicitly. Otherwise, the GPU accelerated subroutines of your Quantum Espresso will not be compiled. And these are instead the options that you should consider where if you're dealing with large problems that require a parallel eigensolver. An eigensolver can work on multiple cores. Okay, now here I'm just showing how Make.Inc should look like for an Intel-based platform and a GPU platform. Maybe I think Ivan and I can go through this during the hands-on and have a look at this Make.Inc. Okay, so very quickly, this happens so often that I always feel obliged to show this, to mention this. So look at this example. It's really happening quite often. So in the top part of the output, you see the number of nodes that this is very old version, by the way. So this is the number of nodes that Quantum Espresso is using, and it also prints the total number of processes, processor cores that it believes it found. But clearly there is a problem here. There are no 15,000 processes in 12 nodes, right? The problem here is that it is creating 36 MPI processes on each node and using 36 threads on each node. So this is the situation I was introducing at the beginning, with all the OMP threads fighting for the same CPU, and this would make the simulation horribly slow. So keep an eye on this and be sure that the number of threads is what you intended to have. Otherwise, this will take forever. Okay, very briefly, in order to understand if you should use parallel eigensolver and what is the dimension of the problem, you should really check as I told you during this couple of hours, hour and a half, the initial part of the output of Quantum Espresso. Here you have the number of connection states. I think you have gone through this. And in the final part, there is a list of timers that details how time was spent in nested subroutines. So very quickly, the computation of the ground state is what you see here, and forces is, as you can see, quite a fraction of the total time. It is not negligible, so it's fine if you look at it. But if this grows quite a lot, well, it may be that you are working with a GPU with a GPU code where the specific algorithm that you are using is not accelerated GPUs, or maybe you are considering the brand new projection scheme for the FT plus U. So anyway, this is more or less the ratio that you should observe. And then moving to the electron subroutine itself, you can see that most of the time is spent solving the connection problems. And this sum band, you can guess what it is. It's the time taken to sum the bands to generate and symmetrize the density. And again, this is more or less the ratio that you should observe. And finally, this is the time computing the application of the Hamiltonian to the wave function, and this is the time spent so this is, sorry, the Davidson, in this case at gamma point, the time taken by the Davidson iterative diagonalization, and this is instead the dense eigenvalue problem in the subspace that I mentioned before. So if you see this growing too much, well, with respect to this ratio, well, it's probably time to activate a parallel eigensolver. Now, I think I really should stop here. I'm quite late. So I think that is it. And
thank you very much, Pietro. Yes, the topic is quite broad. So yes, you really gave us many hints and you covered the overview of many aspects of HPC. And so I think maybe we have time for one question. Is one of the participants want to raise hand? I could let them speak. And we have a few questions on YouTube. A few of them we have answered in chat. So I don't see any raised hand. If you want, you can also write on the Zoom chat now if you have questions. So, okay, yeah, this is a very interesting question. Can quantum espresso be used with consumer grade GPUs? So I think that, yeah, I think this is a really interesting point because many laptops actually have GPUs. So yeah, it is a good question. Yes.
Yes, this is a question that appears quite often. And the real point here and the answer to this question actually in details, a technical detail of the device that you own. Because the point is that quantum espresso is most of the time is dealing, basically always, dealing with double precision operations. While of course GPUs were originally meant to do graphics, so you don't need a double precision. And most of them are quite weak on double precision operation. And therefore, even if they have performance that is very high and advertised as very high, it could well be that this is the performance for single precision operations that are not what quantum espresso is performing. So the answer is that generally happens that consumer grade GPUs are weak on double precision. But if you really want to check this, you can find the technical details of your GPU and check the ratio between the amount of cores devoted to single and double precision operations. And this is something that also the CUDA, a CUDA utility prints. I think there is also PGI Excel info that is printing this. Maybe we can show this during the hands-on and discuss this further with the output in front of us.
Okay, thank you very much, Pietro. We have to stop now. So if participants have more questions, you can just write on Slack. and we will answer. And of course, if I think if more questions will come, we can continue during the hands-on. So let's have the coffee break now. Thank you, and see you in 10 minutes at 10:30.